ask a facetious
Sure.
one?
Yeah.
May I ask a facetious one?
Sure.
Is string theory correct?
Well, I suppose that as far as it's gone, it's probably correct, but is it relevant to physics?
Yeah, basically I'm asking that.
Yeah, I don't know. There's something about the sociology of string theory that is worrisome. Let me just get rid of this. In that it grew out of the same movement that launched all that bootstrap business.
Oh, Jeffrey Chu and his crew?
Right, Jeffrey Chu et al. I mean, Chu didn't, I don't think it was he really invented, but it was that school of physics. Veneziano amplitude, for example, was the thing that stimulated the original string theory, and this was a movement in which people thought that they could do away with quantum field theory and just emphasize the basic principles of relativistic quantum mechanics, and and Unitarian, and so they emphasized the scattering matrix and the analytic properties of the scattering matrix, and then pretty soon they had results about theories of, so they were dealing with functions of several complex variables, and then there were all sorts of, just in the case of a single complex variable, there were all sorts of neat results about a function that's analytic. And in the case of this attempt to do away with quantum field theory, they had functions of many complex variables, and they really it led essentially nowhere, but then it popped up as string theory in an early form of string theory, and it was meant to be a theory of the
Hadrons, right?
right. And the thing is, it makes some sense as a theory of hadrons. And so it may be that if you have a quark and an anti-quark, the gluons essentially form a string between them, and when that thing spins, it's a relativistic string, and the relationship between mass and angular momentum of a relativistic string is followed by various baryon and meson resonances, and I plotted out some of this in the class notes on for the course 466. The very last chapter, I think, is on, not the last chapter, the next to the last chapter is on string theory, and but it's very elementary string theory, and I worked out.
Which book did you use? Or did you do?
These are just my own notes, and I was sort of drawing from different books.
Well, I think that we're still not yet at the level that we can derive physics from mathematics.
Well, yeah, that never, I don't know if that'll ever happen. It's always a rear view mirror activity. And the problem now is there's no longer any rear view mirror because there haven't been really striking accelerator results for decades. And we'll probably get some we'll most certainly get some in 2, 3, 4, 5 years from the LHC. Let's see, is there any other questions, or should we start this thing, or have you already started it?
We've already started.
Oh, great. All right, well, what I want to do today, and I'm sorry there aren't more people here because the topic is pedagogically useful, namely doing these examples. So let me start, though, by two things that aren't quite examples. But they are examples, but they're not examples of addition of angular momentum. I'll do those later. This is something you've probably all seen, but it's important to see it nonetheless. E to the I theta dot sigma over 2, which of course is the same thing as E to the minus I theta dot S over H bar, since S is H bar sigma over 2. This thing, if you expand it, it turns out to be cosine theta over 2 minus I theta hat dot sigma times sine theta over 2. And the way you see that, the easiest way to see that is to just expand the, well, first of all, to notice that theta dot sigma squared. What is it? Well, it's, let me use the summation convention, okay? If I have an index repeated, it means we sum over it over the relevant range, here from 1 to 3. So we have theta I, theta j, sigma I, sigma j, and that is then theta I, theta j, delta ij plus I, epsilon ijk, sigma k. But now, this part is symmetric in I and j, and this part is anti-symmetric in I and j. And so the epsilon sigma k term cancels. And so this is just theta dot theta, or theta squared, if I take theta equal to the length of the vector theta, which is the square root of the sum of the 3 theta components. So when you expand this thing, e to the minus I theta dot sigma over 2, what you get is 1 minus I theta dot sigma over 2, then minus theta dot sigma over 2 squared divided by 2, and then you get plus I theta dot sigma over 2 cubed over 3 factorial and so forth. And you re-express that as 1 minus I theta dot sigma over 2. And then this is, I'm trying to follow my notes so as not to have any typos. Minus a half theta over 2 squared, and then plus I over 3 factorial. Theta dot sigma over, well, let me rewrite that. Let's see. I theta over 2 squared times theta dot sigma over 2, and then 1 over 3 factorial, and then extra terms. And eventually, you see that this is 1 minus theta squared over 2 times a half, and then over here you get plus, or minus actually, minus I theta hat dot sigma, and then this becomes theta over 2 minus 1 over 3 factorial theta over 2 cubed. And you can recognize these are the first 2 terms of the series for cosine theta over 2. And these are the first two terms for the series sine theta over 2. And if you keep track of all the terms, it of course works out. This is an approximation. And there's a similar. So this is a very well-known formula that you see in all the textbooks. But curiously, I've never seen in any textbook, or it must be in some textbook, the corresponding formula for the three-dimensional case. And in particular, if you take the, let's see, how do I want to say it here? If we take e to the minus I theta dot, and now I'm going to write this as h bar j over h bar, just because I want to get rid of that h bar. So the angular momentum, I'm going to take, in other words, I'm going to have j as in the following way. J, the ij component of the 3 by 3 matrix jk is going to be I epsilon ijk. This effectively is the are the generators in the adjoint representation of SU2, or they're the generators for SO3, either way you look at it. And then if you expand this, what you get is cosine theta minus I theta hat dot j. So j here is dimensionless. Sine theta plus 1 minus cosine theta, theta hat transpose. Or if we say that R of theta is this e to the minus I theta dot j, canceling the h bars, then R ij of theta is equal to delta ij cosine theta minus sine theta epsilon ijk theta hat k plus 1 minus cosine theta theta hat I theta hat j. So this is the 3 by 3 matrix, and you can think of this as either SO3, or you can call it the adjoint rep of SU2. And I worked out this formula actually because I was working on protein folding, and I needed to know how these various parts of the molecule would behave when there were rotations about single bonds, which then rotated the whole rest of the molecule relative to the other part of the molecule. Or rotated one side of the molecule relative to the other side. And now, normally, we don't use this adjoint representation when we talk about angular momentum. We instead make a similarity transformation, and in fact, typically a unitary transformation, so that we have J3 diagonal, whereas none of these guys is diagonal in this case. All right, so those are two examples then. Any questions? All right. Now let's see. I want to figure out what to do next. There's a whole group of things to do. All right, let me start right in with the examples. I had hoped that everybody would be here for the examples. All right, let's first write down the basic rule that's the engine of theorems on addition of angular momenta, and it's J plus or minus on a state Jm is h bar, and then it's J minus or plus m, J plus 1 plus or minus m times the state J m plus or minus 1. And of course, if m is equal to j, we showed that j plus on the state jj is 0. If m is equal to minus j, then j minus on the state j minus j is 0. All right, I think that's good enough. So now let's consider a couple of cases here. In fact, to make this thing more physical, let's suppose we have a proton here, a proton there, and then we have an electron cloud here, an electron cloud there. So this is a hydrogen molecule. All right, so what's going on? Well, if we first just look at the electrons, what we see is that each individual electron is in the state spin up or spin down, and it's easier to write plus minus than 1/2 minus 1/2. And so you can have a state that is plus plus, and this is a state that in fact is angular momentum 1 z with 1 in the z component, and this is the direct product of these two. In other words, this is both electrons have spin up, then the addition of angular momentum gives you a state with m equal to 1. So spin is h bar in the z direction, and that can only be if it is total spin 1. But now we can act on that with j minus, and j minus on 1, 1. Well, according to this rule, this will be h bar square root of 1, and we're going down. So it's 1 plus 1 is 2, and then this will be again 2 minus 1 is 1. So this is a big square root of 2, and it will then be the state 1, 0, because we're lowering m by 1. But then if we write it the other way, it's J1 minus plus J2 minus, acting on these two states, plus plus. And so that is J1 minus on plus times plus, plus plus times J2 minus on plus. Now we've got to apply this rule in the case j equals, this is the case. This plus just means 1/2, 1/2. And so this, the first one then will be, well, for sure it's an h bar. Then it's the square root of 1/2 plus 1/2 is 1. 1/2 plus 1/2 is 1. Minus a half, so that's a half. Okay, times the state, and this would be the state 1/2 minus a half, but that just is the state minus, and then times the state plus. And then the same thing is going to happen over here, so we're going to have h bar plus minus over root 2. So this state is 1 over square root of 2 minus plus 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 minus. And then we have, wait a second, did I get that right? I guess it must be right. All right. Somehow the normalization isn't coming out right. So in other words, what I'm getting from this is that 1, 0 is, I'm getting 1/2 times minus, plus, minus. And it should be 1 over root 2. Does anybody see what I did wrong? Let's just check this part. We've got 1, 1. We're going down. So it's 1 plus 1 is unfortunately 2. And it's 2 minus 1 is 1, so that's the square root of 2. And over here, it's 1/2 plus 1/2 is 1. 1/2 plus 1/2 is 1 minus a half is a half. There's something wrong here. In any event, the state 1 minus 1, of course, is just minus. This should be a 1 over square root of 2. I thought this was so trivial I didn't need to write it down and work it out. All right, let me go around to the next example, but I have worked out in my notes here. And maybe it'll come to us why what we did wrong here, what I did wrong here. So in this case, what I want to do is have, here of course we had J1 equal to a half, J2 equal to a half, so we're adding 2 electrons. Well, let me give you the bottom line here. Since this, let me finish the thing apart from this square root of 2. There's another state which is, as you know, when you add 2 angular momenta, you can get the maximum value of J is J1 plus J2, which in this case is 1. The minimum value is, so this is J max. J min is equal to the absolute value of J1 minus J2, and that is 0 in this case. And so we need a state of spin 0 and z component 0. And so that's got to be a combination of minus plus and plus minus, but it's got to be orthogonal to this. And so the conventional choice is 0, 0 is 1 over root 2 times plus minus 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 plus. So that's the conventional choice. By the way, let me mention something about the convention. The convention is that when you get to this state that is orthogonal to this state, there's of course a choice of an overall phase. You can have a plus or minus out here, or you could even have e to the I theta, where theta is some arbitrary real number. The convention is you pick this case where M2 has been lowered, and you have its coefficient real and positive. So the plus sign comes, it's plus minus, or equivalently, the term that is J1, it would be J1, J1, J2, J2 minus 1 would go there. That coefficient has, that state has the plus sign. So you choose, that's the convention. That's at least the most popular convention. Okay, so now we want to talk about, let me just say something more physically about this. So you've got two choices for the electrons. One is spin 1, and that's a triplet, 3 states, and you have a singlet, 1 state, spin 0, angular momentum 0, and for the spins. So maybe I should keep this spin 0. Now the question is, what do the hydrogen atoms do when they form a hydrogen molecule in the ground state? Well, by the Pauli exclusion principle, which we'll get to later in this course, fermions have to be in an antisymmetric state. And so you can have them on, if you put them in the spin 1 state, then the space wave function has to be antisymmetric. If you put them in the spin 0 state, then the spin wave function is antisymmetric and the space wave function can be symmetric. Okay. But if you put them in the spin 1 state, the spin state is symmetric and the space part has to be antisymmetric. But having the space part antisymmetric basically means that the density of electrons here in the center, just between the two protons, has to be 0. And in fact, that's where you want the density to be high, because that's what holds the thing together. In other words, the electrons try to get as close to the two protons as possible, still respecting the uncertainty principle. So they like to cluster here. But that is in a symmetric state. So then the spin state has to be antisymmetric because the space state is symmetric. So in fact, the hydrogen molecule in its ground state, let me just say this is one more thing about this. The hydrogen molecule in its ground state has basically it's the state plus minus plus 1/√2 for the spins, antisymmetric, times a wave function psi of, say, R1 and R2, which is symmetric. And so that's the ground state of hydrogen. And it's slightly surprising. In fact, I'm embarrassed to mention this, that my physical intuition is so bad that when I started working on the hydrogen molecule, I assumed the opposite. And I couldn't get a good ground state energy. And so then I thought, well, maybe I have it wrong. And then, of course, I kept away. So it is tricky. In fact, I was working with a colleague who's quite distinguished. I won't mention his name at the moment, but he had it backwards. And since I was doing most of the work, he kept it backwards, even when he was talking with other people. And, so it's a little bit confusing, but this is the way it works. Any questions then about this? In fact, this is more general than just hydrogen. You can say that basically a covalent bond between two atoms involves two electrons. They're in an antisymmetric spin state and more or less a symmetric spatial state. Of course, this is way oversimplified when we generalize beyond hydrogen in its ground state. But roughly speaking, that's what these bonds are. So when chemists draw things like C, well, I've got that. N, C, C. This is the backbone of an amino acid, and then you have double bond 0 here, and so forth. And a little bond going off, and a little bond going off there. And I'm leaving out and this one is just on the side chain. Then there's a hydrogen here, hydrogen here. Anyway, so this is the basic structure of an amino acid in the protein chain, and each of these lines is two electrons in this spin state, and more or less a symmetric spatial state. Of course, it's not really symmetric when you have carbon here and nitrogen there, but it's sort of symmetric when you have two carbons. If the two carbons were exactly in the same state, then it really would be symmetric. For example, in a hydrocarbon that might be able to form CH, H, and then CH, H, and then a C here. You can imagine that this bond would be pretty much symmetrical. All right, any questions about that before I get back to the subject? All right, so let's now add J1 equal to 1 to J2 equal to 1. Well, we know we can have the state J equal to 2, M equal to 2, which I can write as 2, 2. And what I'm going to do to distinguish the composite system, that is to say the Jm case, this is Jm, this is the combined, the added state. This is the, in other words, this is the basis where we have J, where we have the eigenstates are, the operators of diagonal are J squared, J3, or Jz if you like, and then J1 squared, J2 squared. I'm going to write them in this form, and the basis states are all 1 plus 0 or minus 1 plus 0 minus, and these are eigenstates of J1 squared and J1z, J2 squared, and J2z. Okay, so this is the top state. The top state is 2, 2, 2, 2 is equal to plus plus. That means spin 1 up, spin 1 up. And of course, I'm talking non-relativistic particle, massive particle. Now we act with J minus. And J minus on 2, 2 is H bar. And now that's the square root of 2 plus 2, that's this J plus M. And then the next one is 2 plus 1, which is 3, minus 2, which is 1. And so on to 1. So this is altogether 2 H bar 2 comma 1. That's what J minus is there. Now this is the same thing as J1 minus on plus times minus plus J2 minus on plus. And remember, this is a spin 1. It's not the electron. It's not the spin 1/2 anymore. So we have plus 0 minus. And now, what does this do? This gives us an H bar. And then the square root. Well, now what we have is 1 plus 1 times 1 plus 1 minus 1, and 0 wait a second, I did something silly here. This is still plus. This should have been a plus. Because we're acting on the state 2, 2, which is the same thing as the state plus plus. In other words, this is J1 minus plus J2 minus on the state plus plus. So this is 0 plus plus plus, and this is then, now what's this? This is square root of 2. So this is H bar square root of 2, 0. Okay. So what that tells us then is that the state 2, 1 is 1 over root 2 plus 0 plus 0 plus. Okay? And now we act one more time. We act with J minus on 2, 1. And following these rules, what we get is h bar square root of 3, 3 minus 1, 2, 0. But then this is the same thing as j1 minus plus j2 minus acting on 2, 1. And that's 1 over the square root of 2, 0 plus 1 plus 0 plus 0 plus. And now, so the only part of this that's really tricky is keeping these square roots right. And I don't know what happened to that square root of 2 there. Has anybody seen where the square root of 2 went here? All right, well, anyway. Okay, so j minus on this, that gives us this is h bar over square root of 2, then the square root of 1 plus 1, 1 plus 1 minus 1, 0, 0. So that's this one acting on this one. And, oh, this is more tricky. I think I skipped a line here, so let me write this down in a little more detail. You see, now we have both of these guys acting on both of these guys. So this is 1 over root 2, and it's j1 minus on plus times 0. And then it's j1 minus on 0 times plus. And then it's j2 minus, here, let me write it a little bit differently. And it's plus times j2 minus on 0 plus 0 j2 minus on plus. So it's actually 4 terms that look like that. And now when we do the arithmetic here, what happens is we get h bar over square root of 2 times, as I said, the square root of 1 plus 1 times 1 plus 1 minus 1, 0, 0. So that's this one acting on this one. And then let me do the right one now. Okay, I'm going to do this one now, where j2 minus hits the 0 state. And what that gives us is the square root of 1 plus 1 times 1 plus 1 plus minus. And then the other two, and so that's square root of 2. And the other two are also square root of 2s. So square root of 2 minus plus square root of 2, 0, 0. And so altogether then, what we've got here is that j2 0 times the square root of 6. So this state 2, 0 then is 1 over the square root of 6 times all this, which is, and the square root of 2's cancel. So we have here then plus minus plus 2, 0, 0 plus minus plus. And right. Okay, so that's the answer there. Now, any questions? Now, as we go down, the next, you can do two things here. You can go down one more time using J minus, or what's probably a little bit easier is you can say, well, 2 minus 2 is obviously just minus minus. Okay. Right, both spins pointing down, and that's argument of 2 in the minus E direction. And then you can act with J plus on 2 minus 2, and that gives you h bar square root, and now you use the other formula, the top formula, and that gives you 2 plus 2 times 2 plus 1 minus 2, and that gives, and that's the state 2 minus 1, and now this would be J1 plus plus J2 plus acting on minus minus, and so that is J1 plus on minus times minus plus minus times J2 plus on minus. Okay. And let me continue this equation up here. So this is h bar square root of 1 plus 1 times 1 plus 1 minus 1, or 2 minus 1, times 0 minus plus h bar, and it's the same thing, say square root of 2 minus 0. So then keeping track of this, what we've got is, this is a square root of 4, so that's 2, and these are square root of 2. So altogether what we get is 2, 1 is 1 over square root of 2 times 0 minus plus minus 0. And this is 2 minus 1, not 2, 1. All right, now this stuff is not complicated, so let's try to get this right. Is there a question? Remember, I have chocolate and other sweets. By the way, did anybody ask a question and not get a sweet last time? I think there might have been such a case. So, is there a question here? All right, we still got to figure out that square root. I'm going to work that one out after class, so we'll hang around after class, unless somebody sees the missing square root of 2 in that first example. I'll do it after class. All right, so now we've got the top multiplet done. We've got the states 2m expressed in terms of the other basis, the plus minus basis. So now what we want to do is we want to figure out what is the state j equals 1, m equals 1. Well, we know it's some linear combination of plus 0 plus 0 plus, because it has to have one state spin up and one state spin, say, sideways. Okay? Because in order to have m equal to 1, this is the only way to get m equal to 1. It has to be a linear combination of these two states. Then it has to be orthogonal to this state over here. Okay. Well, the easy way to make it orthogonal is just put a minus sign here. And in fact, that respects the convention. So this is equal to 1 over square root of 2 plus 0 minus 0 plus. Remember, the convention is that the one that you give the plus sign to is the one in which you lower the second one. Which is kind of the thing we want to do anyway. Okay, so that is the state 1-1. And now we can find the state 1-0 by acting with J minus. So J minus on 1-1 gives us h bar square root of 1 plus 1 times 1 plus 1 minus 1 times 1 0. And that is square root of 2 h bar times 1 0. And now that's the same thing as J1 minus plus J2 minus acting on this state, which is 1 over square root of 2 plus 0 minus 0 plus. And, okay, so what does that give us? Let me go up here with that. That gives us h bar over root 2, this root 2 here, and then a bunch of terms. And the first one is the result of J1 minus acting on this, and this gives us 1 plus 1, 1 plus 1, minus 1 times 0, 0. So that's this term. That's, well, maybe I should have said this. This is 1 over root 2, big parentheses, J1 minus on plus 0. And then, J1 minus on plus 0, and then plus J2 minus on 0, and then we have a minus sign, J1 minus on 0 plus, and then another minus sign, 0, J2 minus on plus. Okay, so let's just make sure this is right. All right, that makes sense. And the first one is this one. The next one, this one here, is going to be square root of 1 plus 0 times 1 plus 1 minus 0 on the state plus minus. And then what we get is a repetition of that. And we notice that this one here is square root of 2, and this one here is square root of 2. So they're all square root of 2's. So this is minus root 2 minus plus. That's when this guy acts on this, that's this term. And then this one is going to be square root of 2, 0 minus, no, 0, 0. Okay, so that's the way it looks all together. Now we see something surprising for the first time in these examples. This cancels this. And so we have the state j equal to 1, m equal to 1. And the state 1, 1 is equal to, wait a minute, that's not 1, 1. 1, 0 is what we're talking about. This one here, we divide by square root of 2, and that just cancels these square root of 2's, and so altogether it's just 1 over root 2 times plus minus 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 plus. Now this looks like the spin 1/2 case, but in fact this of course is m1 is equal to 1, m2 is equal to minus 1, m1 is equal to minus 1, m2 is equal to plus 1. So that's that state. And the next state, j equals 1, m equals to minus 1. Well, this one has to be orthogonal to this state. And so again, we stick in a minus sign. And getting the convention right, we have 0 minus 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 0. All right. Okay, at least the part right. It could be a second convention entering in this stage. Finally, we have the state 0, 0 to deal with. So what is the state 0, 0? So we've got the states for spin 1. We can combine things into spin 1. Now we're going for spin 0. All right. So for spin 0, what can we have?
Well, j equals 0, m equals 0 can be a linear combination of these things.
So why don't you guys, while I go get a drink of tea, why don't you think of the 3 states, or think of all the states you can think of that should be entered. We're going to form a linear combination to make this state 0, 0. Tell me what states would have total m equals 0. You don't have to get the linear combination right, just give me the states. Well, we need m equal to 0. Total m equals 0. Well, let's see then. If nobody's giving me the answer, then there's a real disconnect here.
What you want here is m1 plus m2 equal to 0. And the choices for m1 are 1, 0, minus 1. The choices for m2 are 1, 0, minus 1.
So what are the possible cases?
1 minus 1, 0, 0.
All right.
You've got 1 minus 1.
0, 0. And minus 1, 1.
Minus 1, 1?
Yeah.
Is that what you said?
Yeah. I'm not sure or not.
All right. Is there anything else? I don't think so. But these work. All right. Okay. So, now I wrote it. Unfortunately, I switched notation on you. So let me just rewrite it in the notation that I have been using here. This is plus minus. That's the way I've been writing it, thinking that this was a simple notation. I don't know if it is. In any event, this state has to be orthogonal now to this state, which also has m equal to 0. And it has to be orthogonal to this state, which also has m equal to 0. And it's automatically orthogonal to all the other states, because they don't have m equal to 0, total m equal to 0. Okay. So first of all, we have the inner product. 0 is 2, 0 with 0, 0. So this is our state 0, 0. And what is that? Well, that is, we can leave off the overall factors. That is plus minus plus 2, 0, 0 plus minus plus x
plus minus plus y 0, 0 plus z minus plus. Okay, what does that tell us? Well, this answer here is 0 then is equal to x plus 2y plus z. So that's one constraint on x, y, z. Now, it also has to be orthogonal, though, to the state 1, 0, which is over here. So we have 0 is equal to 1, 0, 0, 0, which is plus minus minus plus on this state. And we can leave out the 0, 0 on the right here, so we just have x plus minus plus z minus plus, because 0, 0 obviously is orthogonal to these and it's not going to come through. And so this one is equal to, says 0 is equal to x minus z. And that's kind of interesting, because if we add these two equations together, we get y equals 0. And this equation tells us then x is equal to z. All right, I screwed up again. So let's see, there are, what is, no, adding these together, you don't get y equals 0. Hello? Yes. 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 Could you do me a favor? Could you fax me the results? Sorry. Two 7 1 5 2 0. Thank you. Sorry about that. Okay. Obviously, when you add these two equations, you don't get y equals 0, which is the wrong answer. What you do is you set x equal to z using this equation, and then you have the equation 2x plus 2y is 0. So x equals z, and x equals y.
Negative y.
Duh. X equals minus 1. Thank you. And looking at the notes, what we find is 0, 0 then is equal to 1 over square root 3 times plus minus minus 0, 0 plus minus plus. Now you can see this obviously works, because 0, 0 is orthogonal to this, because it's orthogonal to this because the plus minuses are symmetric here and they're anti-symmetric there. And here it's orthogonal to this one over here, because you get two pluses from the end terms and one minus here with a factor of 2, and so the whole thing is orthogonal. The 1 over root 3 is the right normalization, because if you just take the inner product with itself, you get 3 1s and divide it by 3. Okay, so that's that example. We'll do this spin 1/2, one that was too trivial for me to bother to work out in my notes after class. And now I think what I'll do is show you something very physical, but a different application of the algebra of angular momentum. And this application was invented, as far as I know, I mean, it might have been invented by people prior to him, but the person who made it, whose name is most attached to it, is Eugene Wigner.
And by the way, I once heard a lecture from him. It was very interesting, but it was a terrible lecture. Anyway, brilliant man, of course, Nobel Prize and all that. Wrote a marvelous book on group theory. It often turns out that people who write very good books give terrible lectures. My own feeling has been that, well, all right, I'll just talk about the dead. Dirac gave a pretty good lecture. I remember hearing a lecture by Dirac years ago, and it was well delivered and quite interesting. His idea was that you couldn't have a number as small as Newton's constant for gravity that was related to the rest of physics, and so it must be that it had something to do with the age of the universe. Well, anyway, that was a big tangent that I was racing for. What Wigner introduced was isospin. And isospin has the same algebra as angular momentum. In other words, I sub I commutator I sub j is equal to I epsilon ijk all summed over k. Jk, not a j, this is an I. Notice there's no H bar here because Wigner decided that, or whoever did this, decided let's not stick in the H bar and then pull it out because it was coming in somewhat artificially to begin with. What Wigner noticed was that the proton and the neutron behaved more or less the same in scattering experiments apart from electromagnetic interactions. And so so he said, well, that the proton then can be a state 1/2, 1/2, and the neutron a state 1/2 minus 1/2. And much later, maybe 30, 40 years later, we came to understand that this was because the proton was a state of 2 up quarks and a down quark, and the neutron was a state of 1 up quark and 2 down quarks. And these up and down quarks behave under the strong interactions pretty much the same way, apart from a very tiny difference in mass. And the neutron and the proton only differ by a few electron volts in mass. One is, 938, the other 939, something like that. And at this time they had discovered the pi meson, and they noticed that there was a pi meson, a pi plus meson, and a pi minus meson. And so these three states were regarded as the state 1, and then plus 0 minus in the notation I've been using, and we call these guys plus and minus. If you keep in mind that we need isospin 1/2 here, isospin 1 there. So these, now you can take two protons together, so now we're getting into addition of, the rule, since the algebra is the same as the algebra of rotations, the algebra of isospin is the same as the algebra of the rotation group. And so what we have is we have the state 1,1, which is 2 protons, the state 1,0, which is 1/√2 proton-neutron plus neutron-proton. This is from the example at the beginning that I screwed up. I didn't have the right 1/√2 here. 1 minus 1 is neutron-neutron. Okay. So there's a triplet here. Okay. But now if you look at the bound states of a neutron and a proton, there's one that's actually stable. And it's called
Proton and neutron? What are you asking?
Yeah, what's the bound state called of a proton and neutron?
Deuterium.
That's right. So this bound state called deuterium, and it's written as D, same symbol as the damn quark, but what are you going to do? Anyway, so this is a neutron-proton state, and in fact, it's the following linear combination: 1 over root 2 Pn minus Np. So this is the isospin 0 combination. And it's a singlet. And what this leads one to believe then is that the interaction Hamiltonian, of course, it's a kinetic part, plus a potential part. The potential part would be some coupling constant G times I1 plus I2 squared, where this is, say, some positive number, so let me write it as G squared. And so what you see here is that if you take in the triplet state, so 1m, this is the three triplet states here, the potential V, I'll call this K V. This V, 1m, is then 1m just I1 plus I2 squared. And so this is 1m just I squared for the combined isospin. And this is then 1 times 1 times 2 times 1m, which is to say 2. And then there's a factor of G squared. So 2G squared. On the other hand, if you take the singlet state, well, that's just 0, 0, G, I squared, 0, 0, and that is just 0. So the energy of the singlet state is lower than that of the triplet state, and that's the basic reason why deuterium is bound, and the other states are not. So it's a state that's antisymmetric and isospin, and consequently it's symmetric in space spin, and so it's, as I recall, symmetric in space and also symmetric in spin, so therefore it's a spin 1. If anybody has a wallet card or something like that, you might check the spin of the deuterium and make sure it's 1. Okay, so that, and notice that this interaction here, if this interaction guarantees that the Hamiltonian commutes with isospin, which is what one expects. Okay, now let me do one more example of isospin. What's the time? Is that 4:47? Time passes when we're having fun. All right, I think I better quit. There's no point. Students may have other. You guys, you want to see the other example, or shall I quit? I think it's better to quit because you may have other classes. What do you think? Or let's vote
Depends on the length. I mean,
it's a page.
I'm okay with it. I don't have to do this.
All right, we'll go on a little bit. So we're considering. Let's consider some scattering. So
So here are two processes. Proton goes to deuterium plus a pi plus. Proton plus proton goes to deuterium plus pi naught. Okay, well, the proton-neutron state, which is, let us say, plus minus, this is equal to clearly 1/2 plus minus minus plus minus plus minus, and which is to say this is 1/√2 times the 1, 0 minus the 0, 0 state. In other words, that's the trouble with this notation. Okay, so this is, in other words, this is the triplet, and this is the singlet of the neutron-proton state. So Pn is a linear combination of the triplet and the other, which is what we saw here. You see Pn plus Np is 1 to 0, 1, 0, and so forth. Okay. So now we imagine that the scattering matrix commutes with isospin. And so what do we have? We have d pi plus SPP is, this is just 1, 1, S, 1, 1, whereas d pi 0 S Pn is, well, d pi 0, this d is an isosinglet, so these are all, this is 1, 1, this is 1, 0. So this state is 1, 0 S Pn, and Pn is this thing, which is 1/√2, 1, 0 minus 0, 0. So this thing is equal to 1/√2 times 1, 0 S 1, 0. And since S commutes with isospin, we can argue that these two states are the same. These two amplitudes are the same. And that is to say, this is the same as that. And so one expects then the cross-section for PP goes to d pi plus divided by the cross-section for Pn goes to d pi 0 to be the ratio of these two things squared, which is to say d pi plus S PP divided by d pi 0 S Pn squared, which is then 1, 1 S 1, 1 over 1/2. Oh, the point is that, let me just, I left out one step. This is 1/√2, 1, 0 S 1, 0, because since S commutes with isospin, it can't change the total value of the isospin. So this term is 1, 0 S 0, 0 is 0, and so this is 1/√2, 1, 0 S 1, 0 squared, and so this altogether should be 2, unless I've inverted the square root. My notes have it the other way around.
No, this is right. Okay, so, all right, so let's quit, and I'll put some new homework. So the homework that's due is due on Monday, and I'll put some new homework. And I think what I'm going to do here is I'm going to give 2 sets of homework problems, because some people can apparently do the homework really quickly, and other people have a different background and do it more slowly, or they have more things to do. So I'm going to have some extra credit problems and some normal problems. And people who just get all the normal problems right will get a very good grade. People who do the normal problems and the extra credit problems, I'll add various pluses to the grade. So hopefully with that. Okay, so now those of you who, let's see, you're going to turn off the machine at some point, right? Those of you